remember with integrals, improper integrals, we talked about them being absolutely convergent. And so with integrals, the idea was that if the integral of the absolute value of an improper function converged, then so did the improper integral of the function itself. And that was because area under a curve is negative. And so the integral of some value k to infinity of f of x dx is always going to be less than or equal to the integral from k to infinity of the absolute value of that function, because this will always be positive, thus creating positive area between the function and the curve. This might have some negative area. So we said that if this converged, so did this. Well, the same is true for series. So if the absolute value of a series converges, then so does the series itself, and we call that absolutely convergent. And if the series itself converges but the absolute value does not, then that series is conditionally convergent. And an example of this would be the sum -1 to the n, 1 over n converges, but, so this converges. The sum of the absolute value of that would be 1 over n, does not. We might want to look at absolute values sometimes because a lot of our tests for series require terms to be positive. So for example, if we had sine n over n squared, well, if I look at the absolute value of that, then I can always say that it's between 0 and 1 for sine. And then that would allow me to use comparison test to 1 over n squared. So we could use, if this converges, definitely this does. If this does, this one may or may not converge. So, oh, I should have read ahead. This is the example I was just talking about. So because for comparison test, I need to have that my function, my individual sequence terms are positive. So I know that the absolute value of sine n over n squared, well, I know that that's greater than 0. I also know that it's less than 1 over n squared. Further, I know that the sum from 1 to infinity of 1 over n squared converges by p-test. So, sum from 1 to infinity, absolute value, sine n over n squared converges by comparison. Therefore, the sum from 1 to infinity of sine n over n squared is absolutely convergent.